All right, the first example is, say, suppose we, so let's do some examples. Sorry, not good idea to use the black ink against this. So example number 1 is, suppose we have 2 reservoirs. So we have, say, or well, 2 systems. One of them is a large reservoir. So I have a large, reservoir at some temperature Tr, and a small system, at temperature, say Ts. Now we are not saying which temperature is bigger or less, and so if I now connect these two, connect the system to the reservoir, what will happen is that after some point, the reservoir still will have the same temperature because it's quite big. So even if it's giving up heat or absorbing heat, its temperature is not going to change much. So we just assume that it's going to end up at the same temperature. But our system, at the end of the equilibrium, so when we bring them together, they will not be in equilibrium, but afterwards they will be in equilibrium. And the system will also end up at the temperature of the reservoir, right? So now the heat that is absorbed or given up by the system would be something like this. So the system, absorbs or gives up, the heat delta Q in this process. It would be proportional to the heat capacity of the system, and the difference between the temperature, right? So this could be positive or negative depending on which one is at higher temperature, right? So now the problem is that we have to compute the entropy of the reservoir, the system, and the combined system, i.e. the universe, at the end of the process. So the problem is that we have to compute the entropy of the reservoir, the system, and the combination of the reservoir and the system at the end of this process, okay? Is it clear what the premise is?
Sir, we are basically calculating an equilibrium, right?
Yeah.
The entropy.
Yeah. Okay, so what's the solution? Let's first look at it roughly in a qualitative manner. And there are 2 scenarios, right? One is that the reservoir's temperature is greater than the system's. So in that case, what will happen is that heat will flow from the reservoir to the system, right? And so this is how heat will, and well, energy will flow in the form of heat. That's what I mean, right? So that means that the entropy of the reservoir will decrease, right? And the entropy of the system will increase. Okay, So here we see that because this reservoir is not isolated from the rest of the universe, its entropy can actually decrease. Okay, so entropy can decrease. And in the second scenario, where the system has greater temperature than the reservoir, the opposite will happen, right? So heat will flow from the system to the reservoir, and the entropy of the reservoir will increase, and the entropy of the system will decrease. Now let's look at it quantitatively, okay? So quantitatively, so by the way, this is from Blundell, so you can check it out later. So let's compute the change of entropy of the reservoir, right? So the change of entropy in the entropy of the reservoir is going to be given by, say, dq by T. But the temperature of the reservoir doesn't really change. So we can factor that out. And this is just dq. But this is just the change in the heat that flows out. And taking care of the signs and blah, blah, this is going to be what? Ts minus Tr over, so this is Tr, right? Tr. Okay, so if the temperature of the system is greater than the temperature of the reservoir, this is positive. That means the entropy will increase. And if the temperature of the system is less than Tr, then it's negative, right? As we qualitatively discussed. Okay? So this is for the system, we have d of q by T. Now the temperature is no longer constant. So it goes from the system temperature to the reservoir temperature. And but dq is C times dt divided by T. And now we have Ts to Tr. And then this is going to be a constant times the log of Tr over Ts. Again, if the temperature of the reservoir is higher than the temperature of the system, then this will be positive, right? And because heat is flowing into the system. If the temperature of the system is greater than Tr, then the log factor is negative, and therefore ds is negative. Okay? So now you can add up the change in entropy. So what is the change in the entropy of the universe? And it's going to be C times log of Tr over Ts plus Ts over Tr minus 1. I think they're making a mistake. No, fine. And we can ask, whether this can be negative or positive. And it turns out that it is always positive. And so there's a graph for this. So what we can do is that we can graph the different changes in entropy, say delta of S, as a function of, say, Ts over Tr. So here we have 0, and because and then this is over here, we have, say, 1. And over here, we have 2. And what happens is that if you look at, so we also have to consider it's going to the negative. And if you look at the reservoir temperature, it's kind of a linear function. So it goes something like this. Whereas the the system, that's kind of a logarithmic function, and it goes something like this. And if you look at the total of these guys, of course, what happens is that when we are over here, it's this thing dominates, but when we are over here, the real line, the line will dominate. So what we have is the change of entropy of the universe is something like this. So it is always positive, okay? Right. Okay, so any questions? I think this is a nice little exercise. Oh, don't, oh my God. My cat loves eating shoelaces. So I have to hide my shoes. And now I just caught him eating my shoelaces. Anyway, sorry about that.
So what is the summary of the system and the universe? Like, I got lost in the middle.
Right. So
I didn't understand.
Yeah. So the system. So basically, the universe here is just it's just a sum of the system and the reservoir, right? That's what we are calling the universe. It's just a tongue-in-cheek way of saying that it's the sum of the system and the reservoir. Okay. So the idea is that both of these guys, as we can see from the expression, so this is the expression for the change of the entropy for the reservoir, and this can be both positive or negative, right? Because depending on whether TS is greater than TR or vice versa, right? So the change in the entropy of the reservoir can be both positive or negative. And the change in the system, entropy of the system, can also be either positive or negative, because this log can be either positive or negative depending on whether the temperature of the reservoir is greater than the temperature of the system or vice versa, right? So here the red line is plotting how the change of entropy of the reservoir changes with the ratio of TS over TR, because in all of this, what we can always set TS to be some arbitrary value, and then TR is, so this is the really independent variable. So, and we see that, this has a negative part and it is a positive part, right? And so let me just label this properly. So this is the change of the entropy of the reservoir. And similarly, this is going to be the change of the entropy of the system, okay? And that has a logarithmic behavior. And that too has a part where it is negative and a part where this is positive, okay? So now the system is, the universe is the sum of the system and the reservoir. And here we see that that is always positive, right? So this just...
If the functions both go to 0 at 1, then wouldn't it touch the x-axis at that point? Or am I looking at this wrong?
Yeah, I had the same question.
No, because you have a minus... Yeah, I mean, this is going to be, so this is what? This is at TS over TR, this is 1. So this 1 will cancel this 1. So this is 0, right? And log of 1 is, log of 1 is, log of
0.
1 is not, no. Yeah, log of 1 is 0, of course. Because, yeah, independent of, so yeah, you're right. Yeah. So this should actually touch. Yeah. Yeah, this should touch the 0, but there's no contradiction there, right?
Yeah, but yeah, I was just wondering.
Yeah. No, that's very good. Yeah, I think I unthinkingly copied this from Blundell, the graph, and the Blundell made a blunder, and therefore, so not that I'm making an excuse, but yeah, you're right. Very good. Thank you. That's awesome that you guys are following along.